This video is about factoring matrices. There are two things that are a little different. The matrices we're going to factor are going to be symmetric, and we're going to end up with a diagonal matrix as in the previous video. Okay, so we're going to have a matrix, but this matrix is symmetric, which means that it is equal to its transpose. Let me scratch that, A transpose. Okay, and we're gonna, so assuming this, we're gonna factor this into three matrices, a diagonal matrix in the middle, X, and the inverse of X. But there's one more thing about this. This X has to have orthonormal column vectors with orthonormal column vectors. And that will cause this matrix to be actually the same thing as X transpose. That is part of the spectral theorem. But we're not going to prove the spectral theorem, or we're simply going to apply it in our factorization of matrices. So we're going to do almost the same thing we did, not quite the same, exactly the same, but almost the same thing in the previous video, where we were factoring, with the difference that this time we're going to make sure those vectors, the column vectors of this matrix, are going to be orthonormal. They're going to be orthogonal. So we just want to make sure they are orthonormal, and that this, the inverse is going to be the same as the transpose. All right, let's start with an example. So example 1 will be 74, 2 by 2 matrix, 74, -6, -6, 69. Okay, so we have a fairly large matrix, and we're going to decompose it into this kind of decomposition. So we're going to go ahead and do the same. We're going to start the same way we did it in the previous video. We're going to find the eigenvalues first, and then we're going to find the eigenvectors. And in the previous video, the eigenvectors were the column vectors of this matrix. There's going to be one difference now, though. Let's see. Okay, so we're going to start out with 74 minus lambda, 74 minus lambda, -6, -6, 69 minus lambda, and we're going to find the determinant of that, and that is going to be those two multiplied together, 74 minus lambda times 69 minus lambda, plus, rather minus 36. I got a little confused with the two negatives, but the two negatives are multiplied together is 36, and we subtract this product. We got to be very, very careful as we go through those computations. All right, so we fold that out, and we end up with lambda squared minus 69 and 74 is 143 lambda. And then we're going to add 74 times 69, which I'm going to do on this calculator. 69 times 74. So 5,106. And then we're going to take away 36. So that is going to be lambda squared minus 143 lambda plus 5,070. Let me double check. Minus 36. I should be able to do this in my head. Yep. And then we want to set this equal to 0 to figure out the eigenvalues. So I'm not going to try to factor this out. That's pretty large. So I'm going to use the quadratic formula. Lambda will be opposite of b, 143, plus minus the square root of 143 quantity squared. 143 times equals 20,449. 20,449. And then we're going to subtract 4 times 1 times 5,070. Oh, I can almost do that in my head because that is going to be 20,000. And then 7 times 4 is 280. In this case, over 2. So that is 143 plus or minus square root of, well, 9. 4 minus 8, well, 14 minus 8 is 6. 3 minus 2 is 1. All of that over 2. And that is one of my favorite numbers, 13. 143 plus or minus 13. Divide that by 2. So when we subtract 13, we get 130. Divided by 2 gives us 65. So lambda 1 is going to be 65. And lambda 2 is going to be the other number. If we add 13, we're going to get 156. Divide that by 2, and that's going to give us 78. Okay. Yes. So we got the two eigenvalues. Now we're going to find the eigenvectors corresponding to those two eigenvalues. Let's see. We want 74, -6, -6, 69, which is the original matrix. I'm going to label this matrix as A. Okay, and it is a symmetric matrix because away from the diagonal, the two sides are the same. So that's what's symmetric. In other words, if you transpose this, if this column becomes the row, so this column is the same as that row, this column is the same as that row. So that's why we have symmetry. Anyway, so we want to find A, B vectors. So we end up with 65 of those, 65 A's and 65 B's. I made a mistake as I was trying to prepare for this video to put 65 and then 78. And of course that didn't work. And I thought, man, that wasn't good. So subtract 74 minus 65 because that corresponds to this 74, which will multiply with the A's. So 74 minus 65 is 9. 9, -6, -6. And then subtract 69 minus 65. That's going to give us 4. I believe that is correct. We'll figure this out. But this time we're going to figure out the kernel of this matrix. So all the vectors that multiply with this matrix, which is not the original matrix, mind, it gives us the vector 0, 0. Those two should be related. I'm trying to think. If we divide by 3, we get, so let's focus on this matrix. Divide the top row by 3, and we get 3, -2. If we divide this by -2, we get 3, yep, -2. So that means they are the same row, basically the same row. And so what we end up with is that 3A, so A, B equals 0, 0. What that tells us is that 3A minus 2B is equal to 0, which means that 3A equals 2B. And I prefer to use whole numbers. See, if I put a 1 for the B, let me do one more thing here. we have 3, negative 2, 0, 0, which means B is a free variable. And typically what we do is put 1 for the free variable. So if we put 1 here, then A would have to be 2/3. And that causes us to have a fraction. I prefer to be fraction free. So I'm going to choose B to be 3. So choose B to be 3. It is a free variable, so it can be anything we want it to be. If that is 3, that means that A has to be 2. So the eigenvector corresponding to the eigenvalue 65 will be 3. Wait a minute. 2, 3. There we go. We can double check. What did I say? It was 2, 3 times the original matrix, 74, negative 6. Negative 6 because of the symmetry, and then 69. Yep. So we better end up with 65 times 2, 3. And let's see if that is true. 74 times 2, 150, 148. And then multiplied with 18. Negative 6 times 3, rather, that is negative 18. And so that gives us 130, which is 65 times 2. Yep, 65 times 2. That's the 130. And then if we multiply 2 times negative 6, that is going to give us negative 12. But then we're going to add 3 times 69. 3 times 9 is 27. Carry 2. 3 times 6 is 18, and 2, 20. And then when we subtract, 7 minus 2 is 5. 20 minus 185. And that, I bet, is 65 times 3. 65 times 3. So sure enough, we get 2, 3 multiplied with 65. So that works. So our eigenvector initially is 2, 3. Okay, we're going to do something else with this one, with this eigenvector. Actually, we're going to modify this eigenvector in a moment. Before we modify it, though, we're going to find the other eigenvector. So this is the eigenvector corresponding to lambda equals 65. Remember, there were 2 lambdas, 65 and 78. So next, we search for the eigenvector corresponding to the eigenvalue 78. So we start out the same way: 74, negative 6, 69, times AB. So this is a new portion of the problem. Still same problem, but a new part of it. And we want it to be 78A and 78B. Let me double check to make sure that we do have the 78. Oh yeah, 78. So 65 and 78. Okay, so we subtract 78 from both sides of the equation, and we end up with, well, 78A, and that is going to give us negative 4. Keep the negative 6. Keep the other negative 6 because we're subtracting 78 from the B portion of this equation. Negative 9. Yep. So AB equals 0, 0. So if we divide this by negative 2, so we end up with 2, 3. Divide this by negative 3, we end up with 2, 3. And then if we continue simplifying, we end up with 2, or eliminating, we end up with this. And then you can make that equal to a 1. Let's stay with whole numbers. This means that 2A equals, well, let's start from the beginning. 2A plus 3B, 2A plus 3B equals 0. And there's a plus here. So 2A equals negative 3B. And we can choose B to be negative 2. Choose B to be negative 2. So that it makes the division easy, because then we can divide 6 by 2. We cannot, yes, we can divide 3 by 2 and we end up with 3 halves, negative 3 halves, but that causes us to have a fraction. I'd rather have integers if we can help it. And it doesn't hurt in this, not yet. Um, in this case, we're going to modify our eigenvector anyway. But let's see. So -2 for B. That means that A has to be 3. So we have the eigenvector 3, -2. Let's triple check. Doesn't hurt to check, and it's a good idea. -6, 69. So if we multiply 74 times 3, 4 times 3 is 12, of course, carry 1. 7 times 3 is 21, so we got 22. And then we're going to take away, no, we're going to add 12 plus 12, that is going to be 234. And that better be 74 times 3, because this is the eigenvector corresponding to 74. And just to double check, 4 times 3 is 12. Wait a minute, where's my, no, the eigenvector is 78. I'm confusing the 74 with the 78. So what is 78 times 3? Is it 234? And I don't know the answer. Let's see. 3 times 78 equals, oh yeah, 234. 234, which is 3 times 78. All right, let's multiply the other one, -6. And then we're going to add -138. -138. So that's going to give us -144. 144. Is that -2 times 78? I don't think so. Did I do this right? -6. Where did I get -6? That should be -18. There we go. Okay, so that's wrong. We should end up, why don't I just do it with the calculator? 138 and 18. 138 plus 18 equals 156. Mind, that should be negative. -156. And that should be 2 times 78. Let's double check. 2 times 78 equals 156. Sure enough, 156. Okay, so let's summarize what we have so far. We got 2 eigenvalues. One of them is 65. And the corresponding eigenvector will be 2, 3. So let's label this as x1. The second eigenvalue is 78. And the corresponding eigenvector that we just found is 3, -2. Now, these eigenvectors are very, very special. They are orthogonal. This multiplied with this, with the dot product, is going to give us 0. Okay, but we want to do more than that. We want to make them normal. In other words, the length of this guy has to be 1. And remember how to do this normal? We divide by its length, because the length of this guy is not 1. Its length is 13. Actually, the square root of 13, because 2 squared plus 3 squared equals 13. And so we are going to have a new eigenvector. Let's label it as y1, an improved one, in the sense that it has a length of 1. We're going to put the 1 over 13, square root of 13 outside. So it is the same vector, except that it is modified by multiplying by 1 over square root of 13. And this is a new eigenvector. This is a new eigenvector, which is improved upon this one because it has a length of 1. The length of this guy is going to be also square root of 13. So y2 corresponding to lambda 2 will be a 1 over square root of 13, and then 3, negative 2. Okay. So now we combine those into one matrix, which is X. See, the way we did this in the previous video is we took this matrix, that was our X. So in the previous video, X was equal to 2, 3, 3, negative 2. Okay. But now we're going to improve this, and we're going to use, there's no 1, just Y. So back here at the beginning, I said X, but after, because we want to compare with the previous video, I'm changing the X into a Y. Same thing though. So there's no index here, no subindex. And we're going to use 1 over the square root of 13 instead. And we're going to have same matrix, 2, 3, 3, negative 2. But now each one of the members will be divided by square root of 13. See, we could write 2 over the square root of 13, 3 over the square root of 13, 3 over the square root of 13, negative 2 over the square root of 13. But I'm going to do this instead. Close this. There we go. What is the determinant of this matrix? Negative 4 minus 9, negative 13. Yes. Negative 13. The reason why I'm bringing that up is because I want to find the inverse of this Y. So 4, well, negative 4 minus 9 is negative 13. So the determinant of Y will be 1 over the square root of 13, because that's a, squared. There we go. Yeah. The determinant of a matrix, if you factor out a scalar, is that scalar as many rows and or columns we have. Yeah, because that's just the way it works. That's one of the properties we saw earlier. Yep. Times 13. So times the determinant of this matrix, which is, well, actually negative 13. So we end up with negative 1. So we're good. We wanted to have a matrix whose determinant was 1 or negative 1. Okay, so now what about the inverse? And we typically go through the process of Gauss elimination to find the inverse of this matrix. That is true. But this matrix is very special, it's orthogonal, which means the columns are orthogonal among themselves, and the columns are also normal. That is very, very crucial, because that means that the inverse is going to be the transpose. So all we have to do is transpose this matrix, and we're going to end up with the inverse. So the inverse is 1 over the square root of 13 times 2, 3, 3, negative 2, because that is a transpose of that. That is symmetric, so that is also symmetric. Well, the transpose is going to be the same. Now, I'm skeptical. Is that really the inverse? Well, we can check. It doesn't take much to check. Y multiplied with the inverse, well, what we think the inverse is 1 over the square root of 13 times 2, 3, 3, negative 2 times 1 over the square root of 13 times 2, 3, 3, negative 2. And let's see if that is true. Well, those two multiply the scalars, and we end up with 1 over the square, no square root anymore. And then let's multiply those two matrices. So that's 4 and 9, 13. 6 minus 6, 0. 6 minus 6, 0. 9 plus 4, 13. Sure enough, that is going to give us the identity because we multiply by 1 over 13. And so those two are inverses of one another. So now our goal is to multiply, rather to factor out A as Y. Originally, I had mentioned X, but I changed my mind because let's reserve X for the previous video where we did not ask the columns to be orthonormal. And now we're asking the columns to be orthonormal. So Y diagonal, Y inverse, which by the way is the same thing as this guy, but transposed, the inverse, which doesn't happen all the time. It happens when we have a symmetric matrix. The original matrix we started working with is symmetric. All right. So what is the original A? 74, negative 6, 74, negative 6, negative 6, 69. It should be equal to 1 over the square root of 13 times 2, 3, 3, negative 2, 2, 3, 3, negative 2. Okay. Then we have 65, 0, 0, 78. I forgot to put the 1 over the square root of 3 in the middle. So let me put that in here. 1 over square root of 13. And then we have 2, 3, same matrix. 2, 3, 3, negative 2. And that's it. So this is the factoring of this into an orthogonal matrix, including this guy, a diagonal matrix whose diagonal elements are the eigenvalues of the original matrix times the inverse of this matrix, which happens to be the transpose of this matrix. And there we have it for 2 by 2 matrix. Okay. Now let's do the same thing with a 3 by 3 matrix. So that's example 2. So A will be a 3 by 3 matrix. It is going to be a little bit simple. I apologize for that because, somebody could say, well, this is going to be a little bit of a lame example because it's almost too simple. But I'm playing it safe right now. Okay, there we have it. So now we got a 3 by 3 matrix, and we want to know how to factor that into a diagonal matrix in the middle, an orthogonal matrix on the left, the inverse of that orthogonal matrix on the right, and it will turn out that the inverse of the orthogonal matrix will be the transpose of that orthogonal matrix. Okay, so let's start by looking for the eigenvalues of this matrix. So we want to find the determinant of the matrix 5 minus lambda, negative 1, O, negative 1, 5 minus lambda, 0, 0, 0, 5 minus lambda. Okay, determinant of that. And we can start by 5 minus lambda times the determinant of this 4, which is going to be, so 5 minus lambda, the determinant of this submatrix, with those 4 elements in it, in that order, will be, well, 5 minus lambda squared, That's not too bad. And then we can do minus -1 times those two multiplied together. Boy, that is confusing, because then we have -0. And by the way, here, when we did this part here, we subtracted 0. So we have -1 times 5 minus lambda. Boy, that is confusing. Let me double check. So the reason why we have this negative is because we're in the second position, and I'm using the matrix of pluses and minuses, plus, minus, plus, minus, plus, minus, and so forth. So that minus corresponds to the position. Then we have -1 corresponding to this guy. And then we have the submatrix, this, with those two elements in the main diagonal and those two elements on the other diagonal. So we multiply this -1, which is that one, with this guy, and then we subtract 0. Okay, so there is, and you can figure out how to find the determinant yourself. Now, we are going to set the determinant equal to 0. So it is in our best interest to not expand everything, but rather to factor everything. So I'm going to do that. I'm going to factor out 5 minus lambda, which is the same in those two terms. So that is equal to 5 minus lambda, bracket 5 minus lambda, 5 minus lambda squared. I know my 5s sometimes look weird. And then we have 1 negative, 2 negatives, 3 negatives. So that is -1. Okay. So keep this guy as is, 5 minus lambda. Foil this out, that's going to give us lambda squared minus 10 lambda plus 25, which then we subtract 1. Keep the 5 minus lambda there. And then we have lambda squared minus 10 lambda plus 24. And 6 times 4 is 24, and 6 plus 4 is 10. So we got it. 5 minus lambda. See, if we expand this and end up with a cubic polynomial, finding the roots of that cubic polynomial could be laborious. We don't want to. Why get into that when we can use this zero product property? So this is going to be lambda minus 4 times lambda minus 6. And again, we want this to be 0. So we make that equal to 0. We do that. It's not like it is always 0. It could be 0, it could not be 0, but we want to make it equal to 0. And we have 4 lambdas, rather 3 lambdas. Lambda 1, I'm going to put them in ascending order, will be 4. Lambda 2 will be 5. Lambda 3 will be 6. So we got 4, 5, 6. Okay, now we got our lambdas. And by the way, that means that our diagonal matrix will be 4, 0, 0, 0, 5, 0, 0, 0, 6. The diagonal matrix will be made up by the eigenvalues. Those are our 3 eigenvalues. Our original matrix, by the way, the trace, which is the sum of the main diagonal elements, is 15. And if we add those diagonal elements, we also get 15. That was no coincidence. That's always the case. Okay, so now we look for the eigenvectors, the corresponding eigenvectors for that matrix. Mind that this matrix, the original matrix, is symmetric. 5, well, this doesn't matter what the numbers are. We couldn't care less for what those numbers are. But this element is exactly equal to this element is equal to that element, and that element is equal to that element, making that completely 100% symmetric. What we mean by that is that this column is equal to this row. Second column is equal to the second row. Third column is equal to the third row. That's the other way to characterize a symmetric matrix, if the columns and the rows are equal in the same order. Okay, so now we're going to look for the eigenvectors. So let's look for the eigenvector corresponding to the eigenvalue 4. So 5, -1, -1, 5. That's a 5, 0, 0. Okay, so we want A, B, C, so that we end up with 4 of those, 4A, 4B, 4C. Okay, so I'm going to take away 4 from here. So we have 1, -1, 0. I'm going to take away 4 from the second one, -1, 1, 0. And you guessed it. Oh, okay. And then let's row reduce this matrix. Let's see if we can do that quickly. So if we add this onto this, oh, we get the 0 matrix, the 0 row. If we add this row onto this row, we get the 0 row. So, and then we can permute those two. So we end up with 1, -1, 0, 0, 0, 1. This one can move up here. And then this one, which would be a row of zeros, can be moved to the bottom. And that's not affected, does not affect anything, because we moved this column to the left. So we end up with zeros, and any movement of zeros and adding zeros to anything is just going to end up with zeros. So that does not affect this column. Had that not been a column of zeros, after moving everything to the left, then we would have to pay close attention to what's going on this column. Close attention. But because we had a bunch of zeros, that don't matter. We have a free column here because there's no pivot here. So B is going to be free. And we end up with, so I'm going to write this here. So A minus B equals 0 because we're multiplying with ABC, which means that A equals B. And C is equal to 0. C is equal to 0. So we have to have two of the same, the first two of the same, and the last one has to be 0. So the eigenvector, which I'm going to label as x1, corresponding to lambda 1, which is 4, will be 1, 1. I can just pick B to be 1, A to be 1. That's simplest at this point. There is no 3 and 2 to worry about, and 0. Now, we're going to change that into a y1 because we want our eigenvector to be normal, to have a length of 1. We don't want it to have a length of, right now, it has a length of square root of 2 because 1 squared plus 1 squared is 2. And then we have to take the square root of that to get its length. So y1, little y1, will be 1 over the square root of 2, 1 over the square root of 2, and 0. Boy, we can just factor out the 1 over the square root of 2 and keep 1, 1, 0. That's a little neater. And that's the eigenvector. And you may be thinking, wait a minute, so there's 2 eigenvectors? Yes, there's an infinite number of eigenvectors. If you multiply this vector by any non-zero element, 5, 7, 18, whichever, that's still going to be an eigenvector. So there's multiple of the same. That's kind of weird. Multiple of the same, because they're just the same multiplied with a constant, with a scalar. So they're the same, but they're not the same because this one is multiplied by this scalar while this one is just multiplied by 1. So, but it has exactly the same direction. We want to use this one because it has a length of 1. And remember, when we are changing bases, when we are changing coordinates, it is in our best interest, absolutely best interest, to keep the vectors that we are using for the change of bases as normal, which means length of 1, because then the physics involved is not going to be affected. You know, we can change the direction without changing the actual length. That's essentially what this is helping us do. All right, so 1 down, 2 eigenvectors to go. So let's go with 5, -1, 0, -1, 5, 0, 0, 0, 5, and the other eigenvalue. So 4, now we're going to work with 5. So A, B, C. Before I forget, let me just write down lambda 1 equals 4, which corresponds to this eigenvector. So let's keep them together. This is going to be 5A, 5B, 5C. I don't know if you can tell, but I'm a little more alive today in this video. And one of the reasons is because I had some diet soda with caffeine in it. Don't tell, but I think it's affecting me. And then I had a chocolate chip cookie before starting the video. So I think that's just that sugar and that caffeine in the diet soda is just kicking in. And boy, but wait until the let down, because you know when that goes away, um, then I'm gonna be all sleepy again. Anyway, let's move on with this. So take away 5 from here, and we end up with 0, -1, 0. Take away 5. Oh, that is interesting. So we're gonna end up with -1, 0, 0, 0, 0, 0. Boy, this is already in almost in row echelon form. Boy, this is very, very intriguing. What does that mean? That means that, I mean, you can multiply this by 1, and rather by -1, and this one by -1. And so when we multiply this with A, B, C, and to get 0, 0, 0, what this is telling us is that B is going to be 0. You know, so when we multiply, this row with that column, so we got 0A minus B plus 0C is going to give us 0. So that means that B has to be 0, or negative B is equal to 0, but we can multiply both sides by -1. And then A has to be 0. And how about C? Well, 0C equals 0, but we're going to achieve that no matter what. So C can be anything. C, in fact, those are pivots. So C is our free variable. C is C. That's kind of weird to say, but C means free. C can be anything it wants to be. There's no restriction to C. See, what we are saying here is that B is restricted to be 0. It cannot be anything but 0. A is restricted to be 0. C is restricted to be itself. Yeah, and you may be thinking, where is that coming from? Because aren't you getting 0C, you know, 0A plus 0B plus 0C equals 0. So we're getting initially, 0C equals 0. But that equation is always true no matter what the C value is. If you put 1 million for C, 0 times 1 million is still going to give you 0. So that means that C can be anything it wants to be. There's no restriction on C. That's what that equation states. If C is 0, no problem. 0 times 0 is 0. If C is 1,000, 0 times 1,000 is 0. So it doesn't matter. So in particular, it can be 1. So we have 0, 0, 1. So our eigenvector is 0, 0, 1 for 5. So for lambda 2, which is 5, the corresponding vector is going to be 0, 0, 1. What is the length of this eigenvector? 1, because 0 squared plus 0 squared plus 1 squared is 1. Square root of 1 is 1. So we can bypass the x and call this y2, comma. So y2 is equal to this. This is the eigenvector corresponding to lambda equals 5. 2 down, 1 to go, because there's 3 eigenvectors. So now we're searching for the eigenvector corresponding to 6, eigenvalue 6. If lambda is 6, so that's lambda 3, we want to search for 5, negative 1. See, if you don't start memorizing your problem as you're working it out, you're not, that's a 5. You're not thinking enough about it. I don't know if that is true. That's true for me. When I'm working on a math problem, just about any math problem, it doesn't matter whether it's elementary or difficult. By the time I work through it, I memorize it, or while I'm working through it, I'm memorizing the problem. In my personal opinion, if I don't get to know the problem very well, then how can I be expected to solve it? Yeah, so that is just an idea. Try to get to know problems, analyze them, check them out. 6C, because we're looking at we're searching for the eigenvectors, so that corresponds to the eigenvalue 6. So this multiplied by 6 should be the answer as multiplying with that matrix. As usual, we take away 6 from this guy, 6 from that, and 6 from that. So we're going to end up with just a diagonal of negative 1s. So negative 1, 0, negative 1, which is the same one, 0, and 0, 0, negative 1. Okay, I think I see where this is going. We can multiply that by negative 1, so we end up with 1, 1, 0. When we add that to this one to that one, we end up with a row of zeros. Multiply this one by negative 1, and we can move those two. So we got 0, 0, 1, 0, 0, 0. We have a free column, which means that B is free, and those two are bounded. So A plus B has to be 0, which means that A has to be the opposite of B. Okay, so if B is negative 1, then A is positive 1. So we can start building our eigenvector x3 as 1, negative 1. They have to be opposite of each other. So if this is 1, this is negative 1. If that was negative 1, this would be 1. And C has to be 0. Because when we multiply with A, B, C, A times 0 is 0, plus B times 0 is 0, plus C times 1 is C, and that has to be 0. So C has to be 0. Okay. I was thinking that's something on the paper, so I was trying to move it. That makes me think of a cat, that is chasing the light. Because the cat, that's funny, the cat cannot, or that laser light, cannot tell that's just a light, so you cannot chase it. I guess you can chase it, you cannot catch it. You cannot catch light. Anyway, see all that soda? I'll tell you, we had a chocolate chip cookie and actually it was a double chocolate cookie. It was chocolate with more chocolate in it. So I think that really made me more active. That is not normal. This vector doesn't have a length of 1. So I'm calling normal a vector that has a length of 1. This is longer. Its length is the square root of 2 because 1 squared, -1 quantity squared, added together gives us 2. Take the square root of that, we get the square root of 2. So we really want y3 to be 1 over the square root of 2, 1, -1, 0. Okay. So let's summarize what we have. We have lambda 1 equals 4. Lambda 2 equals 5. Lambda 3 equals 6. Lambda, well, let's start with the last one we just did. 1 over the square root of 2. So y3 equals 1 over the square root of 2, 1, -1, 0. Okay. Now let me look through my papers to find the other two eigenvectors. The eigenvector with 5, that is an interesting one. That's y2 equals 0, 0, 1. And it has length 1 in it. Yeah, that's interesting. Y1, which was the first one we found, was 1 over the square root of 2, 1, 1, 0. 1 over the square root of 2, 1, 1, 0. Okay, so remember what we're going to do next. Do you remember? We are going to write this. We're going to put them together into one matrix. Yes, which is going to be our matrix Y. At the beginning of the video, I said A is going to be X, D, X inverse. As I was going through the video, I realized this X corresponds to the previous video in which we did not call for the eigenvectors to be normal, much less orthonormal. But this time, when we have symmetric matrices, we automatically are going to get that. Not only we can request that, we can almost automatically get it. I said almost because we have to make sure that the vectors are normal. So we have to divide by their length. So we're going to put this together into one matrix. Now, it is better to have this kind of goofy fraction outside of the matrix. It makes the matrix look a little more neat if we have just whole numbers, integers, in the matrix. And if there's a scalar that we can factor out of all of those, that makes the matrix look a little more efficient. So I'm going to do that here. But there's one problem. I'm noticing this one has a scalar, so and that one does have that scalar that we can factor out of the whole matrix, but this one doesn't. So, and I don't really want to have 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2, -1 over the square root of 2. This one will be fine. This one will be just a 1. But we will have 4 places where we will have the square root of 2. 1 over the square root of 2, that fraction, this funny fraction. So what I'm going to do is change this equal. I'm going to factor out 1 over the square root of 2. And that means that we have to put square root of 2 in here. So when we multiply back together, we end up with a 1. The reason why I do that is because then all 3 of the eigenvectors have a 1 over the square root of 2 factor scalar to them, and that can be factored out of the matrix. So Y will be 1 over the square root of 2. I'm going to write this as columns because here we have the columns 1, 1, 0, 1, 1, 0. Not 0, 0, 1, because otherwise we would not be able to factor out the 1 over the square root of 2. 0, 0 square root of 2, 0, 0 square root of 2, and then 1, -1, 1, -1, 0. Yes. So there we have it. This is our Y, including the 1 over the square root of 2. I mean, this matrix is our Y. Now, you may be thinking, boy, that square root of 2 is not an integer. Yes, it is not an integer. You're right. But that's a price that we pay very happily, because if we did not do that, if we kept this as 1, then we would have to put 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2, negative 1 over the square root of 2, and that will make the matrix look more complicated. Nothing wrong with that. It isn't like we have to always factor things out. It just makes them look a little better. Okay, now this is interesting because this matrix, notice, is not symmetric. Not symmetric. Note, this Y is not symmetric. Okay. Now, in the diagonalization, we want to have diagonal matrix X, or Y in this case, and Y inverse. Now, I claim, and it is a fact, that the inverse is the same as the transpose of this matrix. Well, let's double check. So the claim is that if we do the transpose of this, we will end up with the inverse of this matrix. So, okay, so we're going to check that transpose is actually equal to the inverse. We're going to check that right now. So, because normally what we would do in the previous video is we would find the inverse, you know, by the Gauss-Jordan elimination method. Because in these two videos, we don't really want to use a graphing calculator to find the inverse. Now, if you use a graphing calculator to check your answer, by all means do that, yes. But we really want to go through the motions of all the computations, especially because we have a fairly small matrix and fairly simple matrix. Okay, so I want to check this. So I'm going to multiply this Y with the transpose. If we get the inverse, rather, if we get the identity, that will mean that we have, if we get the inverse, yes. So if those two multiply together give us the identity, that means that this guy is, in addition of being the transpose of Y, it will also be the inverse of Y. Okay, 1 over the square root of 2, 1, 0, 1, 1, 0, negative 1, 0, square root of 2, 0. We're going to multiply with 1 over the square root of 2. And I'm going to write this matrix transposed. So this row becomes the column, second row becomes second column, last row becomes last column. I'm going to try to squeeze it down here because I don't think I'm going to have enough room. Let's multiply the scalars together. So we have a half times, okay, I'm nervous. I don't know if this is going to work. 1 plus 1, 2. So far so good, because 2 divided by 2 is 1. 1 minus 1, 0. 0, 0, 0, 0. All right. 1 minus 1, 0. 1, 0. Plus 1 is 2. Okay, that's good. 0, 0, 0. 0, 0, 0. 0, 0, 0. 0, 2, 0. So sure enough, we got the identity, the 3 by 3 identity. Of course, you guys know it is 1, 0, 0, 0, 1, 0, 0, 0, 1. All right. So now we are ready to finish up this problem. I'm looking for the original problem. Here it is. The original problem is we want to factor out this A into 3 matrices. Y, D, Y inverse, which in this case is the transpose. Now, please, 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 remember that we do not necessarily have the transpose in the previous video when the matrices were not symmetric. This time, the matrices are symmetric. So yeah, so the Y and the Y transpose are going to be the same thing as the Y and the Y inverse. But I was going to say something else. Yeah, I'm going to say it at the end. Okay, so 5, -1, 0, -1, 5, 0, 0, 0, 5 equals 1 over the square root of 2, only because it's nicer. It's going to look a little better. And the Y that we found is, I'm going to write the rows, 1, 0, 1, 1, 0, 1. I'm trying to squeeze it in here. So 1, 0, -1, 0, square root of 2, 0, okay. And then we have our diagonal matrix, which is 4, 0, 0, 0, 5, 0, 0, 0, 6. And then we have the inverse of this matrix, which is 1 over the square root of 2 times this guy, but transposed. So it is, this row becomes a column, 1, 0, 1, 1, 0, -1, 0, square root of 2, 0. And we already checked that this is, well, with this scalar, that is the inverse of this matrix. So there we have it. And I'm going to be asking to write A as Y, D, Y inverse. Well, this is Y, this is D, and that is the inverse. Yep. Okay. Something else I wanted to mention is, notice that this matrix is not symmetric. It is not symmetric. If it was symmetric, those two elements on the extreme corners would be the same matrix. Just like here, this one is symmetric. Those two are the same. Those zeros are the same. Those -1s are the same. And those 5s don't have to be the same. That was just a pure coincidence that all of those were 5s. So this matrix is not the same as this one because this one is not symmetric. The reason why I'm bringing that up is because in our example 1, the two matrices we found, and I noticed that after the fact, after we finished the problem, after we were in this point, at this point, I noticed that this matrix is the same as this matrix. This matrix is symmetric, and not only, yeah, this matrix is the same matrix, but that was a coincidence. Yeah, don't think that you will end up with the same matrix. You will end up for sure with a transpose. So what I want to say is that this is the same as Y transpose. Why? Because this was orthogonal. So all the columns were of length 1, and that's why we factor out the square root of 2. Yep, so this is the kind of question I expect you to be able to do on quizzes or tests or any assessment corresponding to this video. Yep, factoring matrices into diagonal matrix and orthonormal or orthogonal matrices, which means that the columns, in addition to being orthogonal, they are normal, they're orthonormal. Yeah, let me just check one quick thing with you guys. Yeah, this matrix is orthogonal because, well, the length is 1 of each one of the vectors. But in addition, if you dot this column vector with this column vector, you get 0. If you dot this vector with this vector, you get 0. This vector with this vector gives you 0. So every pair of vectors, if you multiply them using the dot product, you're going to end up with 0, which means that every pair is going to be, every pair of column vectors will be orthogonal. Yep, yep. So practice this. I can tell the soda is running out and the sugar in the cookie I ate is running out, so I better stop now. No, that's half joking when I'm saying that. All right, guys, bye.